Sometimes the biggest clues come in the smallest packages. Imagine a simple tube of broth in a lab. Inside, a color change, from plain yellow to this brilliant, shocking pink, can solve a life-or-death medical mystery. So let's dive right into this amazing test and see what kind of microscopic secrets it's hiding.
Okay, so what in the world could connect the gnawing pain of a stomach ulcer with the absolute agony of a kidney stone? I mean, they sound like they're from completely different worlds, right? But believe it or not, they can often be traced back to the same hidden culprit, a tiny microbe that's armed with a very specific and very powerful piece of machinery. And that brings us to our medical detective story. In microbiology labs all over the globe, scientists are basically detectives trying to unmask these microscopic suspects. Their mission is to pinpoint exactly which microbe is making a patient sick, and one of their best clues comes from this one, elegantly simple test. And here it is. This is our key piece of evidence, a humble little tube of yellow broth. Now, this broth contains a chemical called urea, and the whole setup is known as the Urease test. It's a cornerstone of clinical microbiology. But the real show starts when we introduce our microbial suspect. And the results? They couldn't be more different. A negative test is, well, kind of boring. The broth just stays yellow. But a positive test? Whoa, you get this dramatic, impossible-to-miss shift to a bright, vibrant pink. So the big question is, what's causing this wild transformation? To really get what's happening, we've got to look at the chemistry behind that color change. This is where we break down how it all comes down to one single key player. And here it is. Meet urease. Urease is an enzyme, which is basically a microscopic molecular machine. Its whole job, its entire purpose, is to find molecules of urea, which is a super common waste product in our bodies, and just break them apart with incredible speed. Okay, so here's the play-by-play of the chemical reaction in that tube. First, the urease enzyme grabs a urea molecule and just rips it in two. This split releases a huge flood of ammonia. Now, ammonia is a strong base, which means it starts making the liquid around it really alkaline, really fast, causing the pH to skyrocket. And the moment that pH level climbs past 8.1, bam, a pH indicator in the broth, called phenol red, instantly flips from yellow to that vivid pink. It's such a clean, elegant chain reaction. So, just how important is this little enzyme to certain microbes? Well, get this. For Helicobacter pylori, that's the bacteria famous for causing stomach ulcers, urease can make up a mind-boggling 10 to 15% of its total cellular protein. This isn't just some side hustle for the bacterium, it's a massive, critical part of its survival strategy. So how does a microbe even build a machine this sophisticated? Let's go a little deeper and look inside the urease engine. Because making this enzyme isn't a simple one-and-done deal. For the cell, it's a major construction project. See, it's not just one gene making one protein. Bacteria are super efficient. They organize all the instructions for big projects like this into what's called an operon. It's like a whole toolkit of genes that all work together as a coordinated team. And the team that builds this urease enzyme, it's highly specialized. I love this part. You can think of it like a high-tech construction crew, or maybe even a Formula One pit crew. Every single gene has a critical job. You've got Ura A and Ura B. They're the ones building the main chassis, the body of the enzyme. But, a car body without an engine is useless, so that's where the accessory proteins come in, coded by Ura E, F, G, and H. These guys are the specialists. They're like the pit crew that grabs these supercritical nickel ions and slots them perfectly into place to fire up the engine. And then you have a specialist like H. pylori, and it's got this extra piece of gear, a gene called Ura I. This thing is genius. It builds a special emergency gate that only opens when acid levels get life-threateningly high. And when it does, it floods the cell with urea, the fuel it needs to survive, right at the most critical moment. Now, just like the enzyme is complex, the ways we detect it can be too. So here we'll see how microbiologists act like detectives themselves, choosing different tools to get more specific clues about their microscopic suspects. The secret here really comes down to the recipe of the test media. On one hand, you have something called Stewart's broth. It's packed with chemicals called buffers, which means it's really resistant to pH changes. Only a microbe that produces a massive, explosive amount of ammonia, like Proteus, can make enough to turn it pink. But on the other hand, you have Christensen's auger. It has very few buffers, making it way more sensitive. This lets scientists spot not just the aggressive guys, but also these slower, more subtle ones that would have been completely missed by the other test.
All right, so now that we know how the test works and how it can be tweaked, let's meet some of the actual microbes it helps us identify. It's time to check out the villains and a few surprise heroes.
So here's our rogues gallery. You've got Helicobacter pylori, using its rapid urease ability to cause stomach ulcers. Then there's Proteus mirabilis, a hyper-rapid producer. Its urease activity is so ridiculously intense that it actually causes minerals in your urine to crystallize into painful kidney stones. And it's not just bacteria. The fungus Cryptococcus neoformans also uses urease as a weapon to help it cause a deadly form of meningitis.
So how does a microbe really use this? Well, to survive in the stomach, which is basically a pH 2 acid bath, H. pylori needs to create its own personal force field. By constantly breaking down urea, it literally surrounds itself with a neutralizing cloud of ammonia. It's a chemical shield that lets it just chill out and thrive in an environment that would kill almost anything else.
But here is a fantastic twist. In our mouths, urease can actually be a good guy. There are certain friendly bacteria living on your teeth that use urease to break down urea that's naturally in your saliva. The ammonia they make helps neutralize the corrosive acid that cavity-causing bacteria produce, which actively helps protect your tooth enamel from decay. So the very same enzyme can be a villain in one place and a hero in another. It all comes down to context.
But of course, the microbial world is never black and white, or in this case, yellow and pink. So for our last section, let's go beyond a simple color and look at one final fascinating little wrinkle in our story.
So up until now, it seems pretty straightforward, right? Pink means it's urease positive. Yellow means it's negative. So if the tube stays yellow, case closed. The microbe just can't use urea. Simple as that.
Well, you probably guessed it. It's not quite that simple. There's one more layer to this mystery.
It turns out that some bacteria that test negative actually have a secret backdoor method. It's called the UCH pathway. This is a completely different, much more complicated way to break down urea. It's a two-step system that uses a lot more energy, and because of that, it produces ammonia way too slowly to ever overwhelm the buffers in our standard test. It never triggers that pink color change. So, a microbe can be totally capable of using urea, but still show up as negative on our classic detective test.
When you think about it, a simple color change in a little tube tells us so much about the invisible world all around us and inside of us, from what's causing an ulcer to how a kidney stone is formed. But it's also a great reminder that for every answer we find, the microbial world has 1,000 more secrets hiding just below the surface. It really makes you wonder, right? What other huge secrets are out there, hiding in plain sight, just waiting for us to find the right test to bring them to light?